This video covers the last part of Chapter 2. One of the things in Chapter 2 that it talks about is different numerical techniques. Numerical techniques are tough programming problems, programming that you want to solve something, some kind of a scientific or an engineering problem mathematically. So the numerical technique is what the program employs to solve the problem. This is actually a very active research area to make very good numerical techniques. So the first numerical technique that we will introduce in this textbook is called a linear interpolation. So a linear interpolation is basically having data. We have data here in this example, and you want to figure out what was happening at some intermediate data point where you didn't take a measurement. So in this data, I took measurement at time equals 1, 2, 3, 4, 5 seconds, and I got the temperature at 1, 2, 3, 4, 5 seconds. But now I'm curious, what was the likely temperature at time equals 2.6 seconds? And so we can make a straight line interpolation or a linear interpolation. So I draw straight lines between my data points, and I do a straight line calculation to figure out the likely temperature at time t equals 2.6 seconds. The book has some messy formulas I'm going to go over in a moment, but just to show you something else, this was a linear interpolation, and that fits pretty well what's going on that we're going to do. But that's not all you can do. They mention cubic splines. We're not going to derive cubic splines right now, but I want to show you some of the effect of that. So I'm using Excel. So here in Excel, you can use a different program if you want, but Excel is a pretty nice program as an engineer for plotting your data. I can tell you that in my 20+ years of being an engineer, I have used Excel extensively to plot my test data. So anyway, I have some test data that I made up here, time and some temperature. So I can now plot it. Excel lets me plot very nicely. So the one that I want to plot is called a XY scatter plot. That's the one I want because I have basically X data and Y data. So I'm going to insert a XY scatter plot, and I have a choice here of connecting the plot with curvy lines, connecting the plot with straight lines, or just plotting the data points. Since I want to see the data points and I want to connect my data points with a straight line and then do a linear interpolation, I'm going to select this option. So there's my chart that doesn't have any data on it yet. So I have to select data. You may think it's funny that I'm doing an Excel demo for you on this video, but starting the next chapter, Chapter 3, we are going to have data that our program will process in some way, and we might have to plot our data. Now, today I'm showing you Excel. Your book mentions using MATLAB, so I will also show you MATLAB on a different video. There is also a Google equivalent of Excel that is free if you don't have Microsoft Office installed on your computer. Okay, so it says I have to add some data to my chart, so I click Add. I want my X values. Click right here. I can go over and just plain old hold down my left mouse key and select the data. It goes right there. Click here, and now I need my Y values. Do the same thing. Click here. I have Y values. Oh, it's plotted already. And I can even give it a name if I want. I'm going to call my series temperature. Type that in. So say OK. So there's my plot of data. Just some arbitrary data, and I could choose to do a linear interpolation between some of these points. Now Excel is kind of nice because it lets you look at the effect of different curve fitting functions. Linear interpolation is a curve fitting function. So if I go up to my chart here and I right click on it, I can do a thing called add trend line. And I'm showing this to you just to give you an idea of what other numerical algorithms exist to fit curves and lines to your data. So add trend line. Okay, so here's a linear trend line. That's a linear interpolation, basically. Actually, they're probably using a cubic splines algorithm to do that. But see, I get a line here that's a straight line fit to the curve. I can play games. I can try an exponential fit. A slight curve occurred. Logarithmic. Logarithmic fit didn't look very good. A polynomial fit didn't look so good either. So it says polynomial of order 2. That means something that has a squared function in it. So maybe if I make it a higher order polynomial, I can get a better fit. And yeah, I can. So that's starting to look like a better fit of the data right now. I can do a power fit. That doesn't look good. And then another thing, which your textbook is going to cover soon, called a moving average. It always starts a data point ahead because it has to average these 2 points. Right now I'm averaging 2 points. Average these 2 points, put out a data plot. Average these 2 points, put out a data plot. And it's works something like that. Another sort of nice thing, let's go back to linear. The Excel will give you an equation for that linear line, but Excel will not do the interpolation between data points. So I just showed this to you to give you an idea of that there are many different ways to do a curve fit to some data, which is a very common task in engineering world. So I can do one more thing. I have a linear fit and it will actually let me display. I clicked display equation on chart, close that up, and it actually gave me a y equals mx plus b equation of a straight line right there. So pretty cool. So anyway, keep Excel in mind because your programs are going to make data, they're going to process data, and you are going to need some way to plot our results from time to time. So back to this problem in the textbook showing you what a linear interpolation is. So the problem is I have some data points and I want to say, oh, what was my temperature at t equals 2.6 seconds? So I note that I know this data point is 260. I know this data point right here, it's 368, and I want to know something in between. So I wrote down these data points. Your textbook also has it on page 54. Page 54 has this problem, but I just want to make sure that this chart is clear here. So this is A, this is f of A. So this would be A right here. This is A, and this is f of A. So really, A equals 20, and f of A equals 60. So A is time, and f of A is temperature. F of anything is f of A, f of B, f of C is temperature. And so the question is, what is the temperature at time equals 2.6 seconds? Or in other words, in the equation that your book gives you, what is f of B at B equals 2.6 seconds? So let's go back and we'll do that problem. So if I use just the equation in the book, it's that a little bit ugly. It says f of B equals f of A plus B minus C over C minus A. And this is probably how we would program it algorithmically as well. F of C minus f of A. So looks kind of like a ugly equation, but let's just go look sort of how it means. So f of b is right here. This is the thing that we don't know, f of b. So I'm just going to say temp equals, so f of a is 60 degrees plus, so b minus c, this is b, this is c, so, or b minus a, I wrote it wrong, b minus a. B minus a, 2.6 minus 2.0 over c minus a, 3.0 minus 2.0 times f of c, which is 68, minus f of a, which is 60. And you go ahead and do that, and you actually get the answer is that the temperature was likely 64.8 degrees. So kind of a not nice formula, but I'm going to show you the way I learned it in school. I learned it a little bit as a pattern, so it might be helpful to you, it might not. So what I do is I say I have a difference of 2.6 between these two numbers, and I want to know a difference between these two numbers. So I just do it by ratios, but I also know the difference between these two numbers and the difference between these two numbers. So I would write ratios. 2.6 minus 2.0. This is actually a consequence of similar triangles. 3.0 minus 2.0 equals f of b minus 60 over 68 minus 60. Now, this is how I solve it mathematically on paper. This makes sense to me. I have a 0.6 equals f of b minus 60 divided by 8. So multiply both sides times 8. You get 4.8 equals f of b minus 60. So solving for f of b, I do indeed get the same answer of 64.8 degrees. So, but a point I should make is that if you had to program it, you would have to come up with an equation like that to program it. On paper, I see it pictorially as ratios, and I can remember what to do. But this is how you would program it. So the next thing I want to talk about at the end of Chapter 2 is math functions. So with just putting the preprocessor directive include standard IO.h, you can add, subtract, multiply, divide, and you can find the modulus, and you don't have to add anything more. If you want to do more complex math functions such as trigonometric or logarithmic, exponential, then you need to put in your code the math.h preprocessor directive, and then you can use these other higher order math functions. C does all of its trigonometric functions using radians. So recall that there's 180 degrees in pi radians. So here are your conversion factors. If you have theta in radians, or you want theta in radians, it's degrees times pi divided by 180. If you're using the sine function in a program, like here I want to find the sine of theta radians, sine of, or here's sine of 3.141. This part of the function right here, the value that you're passing to the function for the function to evaluate, these are called the function arguments. Your book kind of loosely says that the function, the stuff in the parentheses contain inputs to the function, which are called parameters or arguments. There is a difference between parameters and arguments. The parameters we'll learn about when we start writing our own functions, but right now you could say, for example, this is a sine theta function. Theta could be the the function's parameter, but you're going to pass a value like 3.141 as an argument to the function. More on that later. I'm just pointing out that on page 61, arguments and parameters are not the same thing, even though the textbook uses it kind of loosely together. So let's do an example. Okay, so I have some code here. In my code, you can see that I now have besides the include standard IO header, I have an include math, and then I can define a symbolic constant with a preprocessor directive as well. So anywhere in my program that needs pi with a capital letters because it's a constant, anywhere I need pi in my program, it's already been defined up here up in the preprocessor directive areas. So all of my program can now use the constant pi. So I declare two doubles, theta in radians, theta in degrees. I like putting that it's theta and angle and making sure that I put the degrees as part of the variable's name, the identifier. So here's my rest of my code. I'm going to ask the user to enter theta in degrees, and I'm going to convert it to radians and put out the answer. Now this line of code down here, line 19 and 20, I say the sine of so many degrees, whatever I have gotten from the user, equals what? And then I'll output that answer. So other little bits about this code that I want to make sure everybody notices is that I got a number from the user with line 15, the line 15 where it asks the user to enter some degrees. So user enters some degrees, 30, 45, whatever. Stores it in this identifier called theta degrees. But notice I have declared theta degrees to be a double, and I've used the long float LF, that's not 1F, that's LF, long float format specifier. Then declaring everything in doubles and using long floats, everything will be compatible, and you won't get those funny storing of zeros and that you got in the last homework, or the homework before, I think it was. So all these places that they don't say 1F, they say LF for long float. That gives me the full 64 bits to store the number. And it's also compatible with finding the sign of something, because sign, all of these math functions are double precision. So other little interesting thing about this is trying to fit everything here with these print statements was too long of a line, and you wouldn't be able to see it on your screen. So I indented it and continued the statement on this line below. That is perfectly acceptable. It's readable, but make sure you indent. I didn't do anything special with this end of line. I just continued to the next place. If I broke up a long string phrase, I'd have to break it up with quotes. I think I showed that example previously. And then over here, I didn't use an identifier, but I actually did the calculation, sine theta radians, and theta degrees will go in this format specifier, sine of theta radians excuse me, will go in that format specifier when I run the code. So let's save that. I'm going to go ahead and compile it. My program was called Math Examples, so I'll compile it, run it. Please enter angle theta in degrees. Let's say 45 degrees. So 0.785 radians equals 45 degrees. That's lovely. And the sine of 45 degrees is 0.707, and it, etc. It calculated it very nicely. That's 1 over the square root of 2. Now let's say I wanted more precision in that answer. I could have output something like 2.7 let's make it big. 15. So let's run that, see what happens. So that says, well, let's see what it shows. I think that's the best. Compile, run it. I'm going to use 45 degrees again. And so now you see, I think that that should be 15 places out past the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, indeed, that's 15 places out past the decimal. So specifying 2.15, 2 is the how many places you are allowed to have before the decimal, and then 15 places after the decimal. So that worked nice. The very last thing in this chapter has a short blip about character functions. There's a lot of things that you can do with single characters. It's unfortunate the book introduces to you all of these different character functions, but then none of the homework problems reflect using character functions. So I suggest to you that you take a look at them, play with them, see what they do. Until such time as that we need to write programs using these functions, I'm not going to worry about it too much. So this concludes the end of chapter 2. It is time to move on to chapter 3.